Hi guys. So in the first video on this channel, we are going to convert the style transfer paper, the very famous style transfer paper, into code because there are a lot of intricacies in this paper. There's a lot of things we can actually understand when we convert this paper into code. It teaches us a lot about custom training, about gradient tape, about how to use optimizers, about custom loss functions, and a lot of stuff like that. So this is the paper which we are going to convert to code. So I would strongly recommend everyone to look at this paper. It's a very famous paper. It's one of the OG papers based on style transfer. So what we're going to do, so what style transfer is basically is we give a content image like this, and we give a style image like this, and we kind of get an output where the style images kind of influence the content image in some sort, and then you can see how we can generate some really cool artistic images. So these are a few examples. Like this is the one content image, and for different style images, we can see what kind of outputs we are getting, right? So if we come down, we can see a lot of really scary equations. And yeah, for example, this loss function, this is the content loss function. Then this is the gram matrix. This is a style loss function. Um, and when we come down, this is the final loss function. And yeah, so that wraps up the whole paper. So we'll try to see how we can implement all these things in code in TensorFlow. I'm going to be using TensorFlow, and that to be more specific, TensorFlow 2.0, and which has eager execution, which makes it much more easier to use than in TensorFlow 1, where we had to do sessions and all that stuff. So yeah, this is a basic intro to the paper. We'll be implementing the entire paper. So be sure that you have read the paper at least once, or at least gone through the function. I'll be explaining the meaning of each equation as well, so that there's more intuition behind writing code and not just writing random code, right? So that will give you a good intuition behind the code. All right. I hope you guys have gone through the paper once and understood, have a basic intuition of what's happening here. So let's start by the classic stuff, the imports. So there are a few important imports here. Import TensorFlow STF, import NumPy as NP, import matplotlib.pyplot as PLT. So this completes like the holy trio of imports. This is like you will see this everywhere, legit. You will see this in every deep learning project if it's in TensorFlow. And so let's just import a few more libraries. Import CV2. CV2 or OpenCV is an image processing library. It's used to do a lot of really cool image processing tasks. And we're just going to use it for basic stuff like changing the color space or maybe reading an image or something like that. And we are going to import PIL. Again, PIL is again an image processing library, which is used to do a lot of stuff. You guys will be seeing what we're going to do with these in the later stages of the video. And one last import is from TensorFlow.keras import model. Again, we'll see what this does. This is what we use to create our model, which is basically the VGG, right? All right. So now we've imported model. So now what we're going to do is let's just try to understand. So we're going to use VGG, right? So let's try to understand how to call a pre-trained VGG. So we're not going to train our own VGG. We're not going to do all that complicated stuff. We're just going to take VGG, which is pre-trained on ImageNet dataset. So ImageNet is a really huge dataset, which has a lot of images around. There are a lot of classes in it. So we're just going to use a pre-trained VGG. So how do we do that? So there's something called as applications in TensorFlow.keras. So it's basically a callable module inside Keras. So how we call that is VGG is equal to tf.keras.applications dot v. Yeah, so you can go for VGG 16 or VGG 19. That's totally up to you. So I'm just going to go with 19. And inside this, there are two parameters which we need to give. One is include top. I'll explain what it is in just a minute. And next is weights. So it's going to be ImageNet, obviously, because we need the weights, pre-trained weights of ImageNet. Now, let's try to understand what include top is. What is this whole thing going on here, right? So for VGG, sorry, for layers in VGG.layers, print. I'm just going to make an F string so that all the Python geeks are really happy. And let's format it. So what we're going to do is we're going to put layers.name and layers dot output underscore shape. So now when we run this cell, you can see that it might take some time to download, which is cool. It happens for the first time after it gets cached. So, and it's really fast if you look carefully. So now what we can see here is it has downloaded pre-trained weights from this link. So if you click this link, it'll automatically start downloading it as well. So we can see that this is the basic, these are the layers and these are the output shapes for each layer. So we can see that after this block 5 pool 1, which is basically a pooling layer, we can see that there's a flatten, there's a fully connected 1, fully connected 2, and a final output layer. So this is because I gave include top is equal to true. So what if I give include top is equal to false? So if I run that again, we can see that the last layer is block 5 underscore pool, and there are no dense layers after this. So this is very important to understand. This is what include top does. These are small integrity details which people kind of miss out when they're trying to do deep learning. So all right, once we have this, so I'm just going to keep it as true. So it really doesn't matter as of now because we just need the convolution layers. I'm just going to keep this because I have the weights downloaded already and I don't want to download it again. Now that we have the VGG ready, so let's try to understand what this gram matrix is. This equation looks really complicated, right? So let's try to break it down into much simpler terms. Let's try to understand what I is, what J is, what C is, what D is. Let's try to understand all these things. So let's just take a simple example here. So for example, let's just take block 3 pool. Okay, so we can see that the output is 28 cross 28 cross 256, right? So let's come down, let's try to understand, let's try to break this down, right? So this means the output will be something like this. It's going to be a cube, not a cuboid. And pardon my drawing skills, it's probably appalling, but okay. So 28 cross 28, and this distance will be 256, right? Not distance, I meant the width. So there are 256 number of filters. So let's try to understand this properly. There are 256 number of filters here. That is the depth of the output, right? And this is 28 cross 28. That's the dimension of each filter. So what a gram matrix does is it tries to find out the correlation between two filters, right? So basically there is one filter. Let's just take a simple example. There's one filter which detects, let's say, brown stripes and black stripes, brown and black, a combination of brown and black stripes. Wow, that's a tongue twister. Okay, so there's another filter which detects eyes, something of the shape of your eyes. Okay, so let's say both these filters get activated together. So we can say there might be the presence of a lion, right? That's how filters correlate with each other. So if two filters have strong correlation, we can see that, so if it's a tiger, then the two filters of black and brown stripes and the filter which detects eyes, both of them will have a very strong correlation. So a gram matrix is basically a measure of this correlation. So what I does is, I is the pixel which we are going to take. So there are 28 cross 28, right? So there are 28 pixels in this direction and there are 28 pixels in this direction. So I is that. So I is which pixel we are talking about. Now when we see J is which filter we are talking about. So there are 256 filters here. So J is which filter we are talking about. And now C and D. So C and D are basically, let's say I give an input of, let's say, so let's call this C, and let's say I give another D of, let's just forget the dimensions for now, of some dimension which can change variably, and let's just I give another input D. So we are talking about C here and D here. So we are going to give IJ which belongs to this D and the I and J which belongs to C. All right. So that's what's meant by C and D here as well. Now what I and J means is nothing but the capital I and capital J means this 28 cross 28, this number, the height and the width of each filter in that entire block. So let's say we have so in simple words, if this is one block of yours and let's call it C, then capital I is 28, capital J is 28, and there are 256 filters in it. So in short, this is the best explanation. This is the most intuitive explanation I can give for gram matrix. I'll link a small tutorial video in the description. You guys can check that out. It's a pretty cool video explanation where he manually calculates a gram matrix. So if you guys want a more mathematical approach, you guys can check that out. Now that you know the basics of gram matrix and you have an intuition behind the gram matrix, let's try to code it out. So let's just make a function of called gram matrix, and it takes an input tensor. Now, what we do is I'll show you how TensorFlow really can boost your deep learning experience. This function looks kind of complicated, and you might wonder, wow, we might have to run for loops and iterate through pixels and then multiply each pixel and then find out correlation and then take that as a gram matrix. We don't need to do all that. TensorFlow has this library called linear algebra, and it has some really, really cool functions. I'll show you how it works in just a minute. So let's say the result is equal to tf.linalg. linalg stands for linear algebra. And then we have a function called einsum, einsum, or however you can pronounce it. So now how you do here, how you use einsum is, let's say the first multiplication here is ijc, right? So ijc, and so this should be inside quotes because it's a pattern, right? ijc. Now the next part which we can see here is ijt. So you just type ijt, all right? And the output which you are trying to expect here is cd. So you're going to write CD, right? But in deep learning, things really don't work like this. Things work in batches, right? There's always a batch. We always give batch inputs. Like the batch size can be 1, but it's still going to be a batched input. So just to handle that, we're just going to give batch here, and batch here. Now we have to give inputs of what is C and what is D. So both will be our input tensor. So both will be our input tensor. And once we have that, we can say that gram matrix is equal to tf dot expand dimensions. So expand dimensions basically adds a batch to the outer layer, because once we calculate the linear algebra sum, there's not going to be a batch anymore. So we're just going to expand dimensions to create that batch outside. And what we do is we just give the result to this and say axis is equal to 0. So along the 0th axis, we are just going to add one more batch to it. So once that is done, now we need to find out what is I and what is J, right? So let's just say, I'm just going to call it I underscore J just for simplicity. So tf.shape, we're just going to use another TensorFlow function, and we're just going to say, okay, yeah, before that, let's calculate the input shape, what input shape is, right? So input shape is equal to tf.shape, and we're just going to pass the input tensor. So tf.shape. So now we have the shape of this tensor, which we have given as input to the gram matrix. Now we're going to find out what the ij value is, right? So we're not going to use tf.shape here. So sorry. We're going to use tf.cast. We're going to cast that value into a float for more precision and accuracy. So how we do that is shape of 1, because 0 will be the batch, obviously, into input shape of 2. So this is going to be the ij product, and we're just going to cast it into our TensorFlow. We're going to cast it into TensorFlow float 32 type. So we're converting it to float for more precision and accuracy. Right. Now we can just return this. We can just return gram matrix divided by I underscore j. So that completes our gram matrix function. And it's as simple as that. So that's how TensorFlow really helps you while you're doing deep learning, especially TensorFlow 2.0 for that matter. All right. Now everyone is waiting for the model part, right? So where are we going to make the model? We have done all the pre-processing related stuff. So where's the model? Right. So let's code the model right now. So let's just write a function. So I told you we can use the tf.applications, right? tf.keras.applications.pgg19. There will be a small change here, which I'll show you, and I'll justify why I'm doing it. So this is going to be true. It's going to remain the same. But in weights, we're going to give none. I told you we're going to give ImageNet weights, right? So why am I doing this? The reason is that I don't want it to download every single time I run this cell. I don't want it to run the VGG weights, right? I don't want it to download the VGG weights, right? So what I'm going to do now for that is, all right, so I downloaded the weights and now I've uploaded it to my Google Drive. So I'm just going to copy the path here So after doing that, I'm just going to type vgg.loadWeights, and I'm just going to give the path inside that. So once I do that, the VGG class has a function called loadWeights, which is going to take a path of where the weights are stored, and it's going to load all the weights into that variable called VGG, right? So now if you have gone through the paper, you know that the content layers which you're going to work with is block 4 underscore con2, right? And the style layers which we're going to work, there are 5 style layers which we're going to work with. So style layers is equal to, I just have just placed it here so that we don't really need to go through we don't need to type the entire thing again. So the style layers which we're going to use are these, and now what we're going to do is we're going to take out the outputs from each layer. So how we do that is the VGG function, just like how it has a function called VGG class, just how it has a function called loadWeights, similarly it has a function called getLayer. So how we do this, let's just say content output is equal to VGG dot get underscore layer. In that we're going to give the layer name. So now the content layers, there's just one layer, so I'm just going to index it directly without much complications. Dot output, I'm just going to directly take out the output, right? Now for style layer, oh I'm sorry, now for style layer it's not like that. There are 5 outputs because there are 5 layers, right? So for style output, I'm just going to take a function, a list in which I'm going to write vgg dot get underscore layer. Here I'm going to write style layer for dot output for style layer in style layers. So basically what happens here is this style layer is an iterable which belongs to this list called style layers, which we have defined here. So for each style layer in style layers, that is this and so on, it's going to go inside this vg.getLayer thing and get an output, and it's going to get appended to this list called style output, right? This is just a neater way of writing a for loop where we don't write it in different lines. I just wrote in the same line. Yeah. Now we need to pass all these style outputs to a gram matrix. So how do we do that? We have a function called gram matrix which we just defined. So we're just going to leverage that. So let's say gram style output is equal to gram matrix of output underscore. I'm just going to just keep it like that for output in style output. Yeah. So again, output is an iterable which belongs to this list called style output, which is this. So each element inside this list will go through the gram matrix, and the output will get appended to this list called gram style output. Yeah. So now we're going to make a model out of all these things. So the model which we want is equal to model. Please understand the difference between this model and this model. This is just a variable. This is the model class. The model class is exactly what we imported here, right? The model class takes in two parameters as lists. One is the input. Input is going to be simple, the input which you're going to give to the VGG, and it's going to give us 2 outputs. That is content output and gram style output. So I'm just going to copy paste that. Yeah. So once we have this, our model is ready and we can just return the model, right? All right. So that's how you define a model function. This part of the code is the most intuitive part of the code. That's why I'm not going to type it out. I already have it pre-typed. So here, what we're doing, we're not doing anything complicated. So I have a folder called style transfer in which I have a content image and I have a style image. So, and there are some other recordings, just pardon that. And now what we're going to do here is we're just going to use CV2 to read in the images which are in my drive. And then I'm just going to resize them to 256 cross 256. And then I'm going to convert the image to a float 32. So what happens when you convert an image to float 32 is that it basically brings the image pixels into a range of 0 and 1, because normally it will be in a range of 0 and 255. Now it's going to be in a range of 0 and 1. So this is required because the VGG which we have loaded, right, that from the TensorFlow.keras.applications, it takes in inputs between 0 and 1. It expects the float 32 image to come in basically. So once we're done with that, I'm just going to input the style image the same way and resize that to 256 cross 256 as well. And then I'm going to convert that to a float 32. And then I'm just going to plot these two so that we can see both the plots simultaneously. So this is going to be the content image and this is going to be the style image. And once we have that, we can now proceed to write a training loop or a training function, I'd rather say. So before we proceed to the training loop, we need to define our optimizers and our loss function. So for optimizer, I'm just going to go with a simple Adam optimizer, which we call using the tf.optimizers class. And then we're going to set the learning rate to 0.02 as of now. And we're just going to keep a higher learning rate than normal. We'll change it accordingly later. And then we're going to keep a beta 1 of 0.99 and an epsilon of 1 e power minus 1, that is 10 power minus 1. This is the content loss and this is the style loss. So we're going to define both. And if you come to the paper, you can see that there's a part where they say the total loss, it's actually below. Yeah, the total loss is equal to alpha into content loss and beta into style loss. So we're just going to define these alpha beta values here. That is, I'm just going to keep it 10 power minus 2 and 10 power minus 4 just for now. Also, the loss object takes 4 inputs. That is style outputs, content output, style target, and content target. So that is exactly what GA and FP represent. One G is style output, A is style target, and similarly F is style content output, and P is content target. So when we come down, let's try to write these functions down. So content loss is equal to, yeah, let's try to define our content loss. So what we're going to do here is this is the function. So there's a summation where we're subtracting the output from the target from the output and squaring it and summing it and dividing it by 2. I'm going to divide it by the mean because it's a constant and dividing it by constant will not affect the back propagation because the partial derivative of a constant is 0. So it's not going to affect the back propagation. So how I'm going to use that is there's a function called in TensorFlow called reduce mean. So that basically does the summation and divides it by the mean. Now the input for this function will be content output minus content style whole square. I'm going to raise it to the power 2. This is going to be outputs because that's the function, that's the variable which we are passing. Now let's try to define the style function, the style loss. This is not going to be that simple because it's a list, because style targets is a list of 5 elements and style output is also a list of 5 elements. So this is not going to be that simple, but it's still relatively very easy. It's still going to be the same. It's going to remain pretty similar to what we have done as of now. So reduce mean, and inside this, we're just going to write, let's say output underscore minus target underscore, and then we're going to raise it to the whole square. So now what is output and what is target, right? So we're going to write for output underscore comma target underscore in zip. Oh, my bad. In zip style output comma style target. So we're just going to put this entire thing inside a list. So each element will be subtracted with the corresponding element in target. So each element in output will be subtracted with the corresponding element in target. And then we're going to reduce mean on that. And we're going to get a list of 5 elements again. But a loss is usually a number. So what we're going to do is we're going to add all these 5 elements. So how we do that is there's a function in TF called tf.add underscore n. And all we need to do is pass the list to that. Once we do that, we are done. So this is it. Now total loss will be equal to content weight into content loss. Sorry, my bad. Plus so total loss will be content weight into content loss plus style weight into style loss. Once we have that, we can just return total loss. So there you go. That is the loss function, and it's as simple as that to do it with TensorFlow. Just before we write the training function, this is one last thing which we need to declare. So we're going to call the VGG by using the function which we wrote ourselves. That is the load underscore VGG function, this one. So we're going to call that, and we're going to get our VGG model. Now what we're going to do is we're going to pass in the content image, which we have loaded here, this one, and the style image. We're going to pass both through this VGG model. And as you remember, the output of VGG is two. One is the content output and one is the style output. So the content output of the content image will be assigned to content target, and the style output of the style image will be assigned to the style target. All right. All right, now we are done with everything. We can finally write the function for training. And this is really simple with TensorFlow 2. This is really cool function called gradient tape, which can watch your gradients. So how we do that is, let's just write a simple function called train step, and which is going to give it two inputs. One is image and one is which epoch we are on, right? So it's going to take these two images. Now we're going to use TensorFlow. TensorFlow is one of the most powerful tools in TensorFlow 2.0, that is gradient tape. So with tf dot gradient tape, as tape, and inside this we're going to call the model again. We're going to do a forward pass in basically. So output will be equal to VGG underscore model, and we're going to give the image, we're going to multiply it with 255. The reason being that image input which we are going to get is going to be in the range of 0 and 1. So we're going to multiply it with 255 so that it becomes in the range of, it goes back to the range of 0 to 255. You'll get to know the reason very soon, once I get to the next part. So now we're going to calculate loss. So I just copied the equation because I don't want to write, it's really long. So loss is equal to, we're going to call this loss object function which we have defined here, and we are going to give it output of 1, that is nothing but style outputs, output of 0, that is content outputs, and style targets and content targets, though we have defined it on top itself. Once we have all this, we can come out of the gradient tape and we can actually calculate the gradients. So gradient is equal to tape dot gradient, and it's going to take in two parameters, the loss and the image, right? So that's how you calculate how much gradients you need to backpropagate, right? So pretty intuitive, loss and the input image. So once we have that, now let's actually use our optimizer to optimize these gradients and to backpropagate to the image. So optimizer which we have made it opt dot apply gradients, and apply gradients basically takes a single input which is a list of a tuple. So it's going to be a list of a tuple and gradient comma image. So gradient we have calculated here, and image those coming from the function input. So we're going to use that and use the optimizer to apply that. Once we have this, so we're taking out outputs from different layers from the VGG, right? And the activation inside VGG is ReLU. So there might be places where your value of a pixel might go above 255, and this is not wanted. So what we're going to do is we're going to clip this. We're going to clip it between 0 and 1 again, so that in the next training loop, when we multiply it with 255, it's going to go back to a range of 0 and 255. And at the end of every training loop, we'll again clip it back to 0 and 1. It's a very smart strategy to avoid explosion of gradients, right? So how we do that? So you can write a normal function to do it, but I just use the TensorFlow inbuilt function called image.assign, and then within that I'm just going to use tf.clip by value, and in that I'm going to pass in the image, and I'm going to say clip value min is equal to 0.0 and clip value max is equal to 1.0. Once we do that, we are ready to go. And just a small detail if you want, I'm just going to check this. If epoch modulo 100 is divisible by, so basically if it's a epoch number which is divisible by 100, I'm just going to print the loss just to see what's happening. Just if you want to check if the loss is decreasing or what's happening, if you want to keep a track of that. If you print this, you're going to print a tensor. So to avoid that, you're going to use tf.print, and then inside that you can just print loss is equal to. So this is your basic training function. This is going to take care of everything. Now let's try to understand what is actually backpropagating. Right. So before we move forward, there's just one small thing which I wanted to point out. Here in this function, we also need to set vgg dot trainable to false, because we don't want the VGG to be trainable. We want the input image to get changed accordingly and get converted into the artistic form. I'll get into the explanation in just a bit. Okay, so let's start the training process. The code is really simple and redundant, so I didn't want to code it live. I'll just show you how it works. We're just going to define one epochs variable and give it 10 or how many ever epochs you want to run. So then what we do is we make this image variable in which we put in the content image, the image, the basic content image which we have loaded, which you can see on top here, this content image. We are basically going to load that. We are just going to convert it into a float32 and load it into this variable. But in the TensorFlow computation graph, this variable, which is, it's a variable according to Python, but in the TensorFlow computation graph, it's a constant because all the pixel values are the basic pixel values which belong to content image. So it's not something through which you can back propagate. So, and VGG.trainable, we have set it to false. So what is actually being trained here? So we need to make this image in such a way that this image can be trained. So for that, we say tf.variable of image. This list is here is given to make it into a batch. But anyway, so image is equal to tf.variable of image. What this does is that it basically converts this all these pixel points in the all these pixels of the image, all these become changeable. So when backpropagation happens, this image, which has a set of pixels, gets changed. And that's how we make the new image. So at every backpropagation, this image variable in the computation graph will keep on getting changed. And that's how we slowly move towards the final output. So running this for 10 epochs, just 10 epochs, just to see what's happening. So the first epoch is the 0th epoch, right? Because the for loop starts from 0. So we can see that the loss in the first epoch is a very, very big number, and it will keep on going down. So I'll just run this for 10 epochs just to show you what kind of output we can get. And then let's see how it comes out, and we'll improv on spot. All right, so the training is over, and if we have just trained it for 10 epochs, so I've just written some boilerplate code of how to convert a tensor. So this, we have written image is equal to tf.variable, right? So image right now is a tensor in the computation graph. So I've just written some basic boilerplate code here of how to convert in a tensor to a proper image which can be displayed using matplotlib. So this is some basic code, boilerplate code. You guys can just copy it down. There's no point really in going through it. And once I run this, we can get an image. So we can see that it is influenced by style for the most part. I'll just zoom in. And yes, we can see that clearly there is some influence of the style image, and the content image is pretty prominent. But this is not really that good. So we have just trained it for 10 epochs. I'll just change few hyperparameters and I'll try to explain the intuition behind these hyperparameters. And then let's see how this turns out. Okay. All right. So the previous output was not really that, you couldn't really see style transfer being very prominent in it. So what I did is I just made few changes in the hyperparameters. So the first hyperparameter I changed was the content weight. So it was 10 power minus 4. I changed it to 10 power minus 1. I wanted the content to be a bit more prominent, even though I wanted the style to come out well. So I wanted to keep it more prominent. And I also changed the learning rate. I decreased the learning rate to 0.01. The reason behind that is I felt like if you could decrease the learning rate, you could help it converge much slower than what it would converge normally, which will cause it to have a much better blend between the content loss and the style loss, right? Now, also I trained it for 100 epochs. Once we have done all that, let's just run this cell and see what output we get. And there you go. We have a much more style transfer, much more expressive image of style transfer. Again, we can always deny of how good or how bad it is. It's always a very debatable concept. We can see how the style image is actually influencing this, and the content is still there. You can still see the houses, the trees, the valley, but it's really influenced by the style image. So you guys can go crazy with it. You guys can play around with the hyperparameters, make changes, and you guys can see how you can really get very, very cool images from this. So I'll also link the code to Google's Seedbank. Seedbank is basically a collection of really state-of-the-art codes, which is written by Google engineers at Google. So I'll link that below and link a lot of resources, other resources below. So this is how you can basically go about doing a basic style transfer in TensorFlow 2.0. I hope it helped. I'm Siddharth, and I made this video with the help of my friend Tarun. And peace.